in the last lecture we had examined the conditions under which we can use correlations in a balance equation. Okay. So, if you recall that we had derived correlations for or we had presented correlations for low Peclet number, high Peclet number, heat and mass transfer, and those correlations are actually derived assuming that the system is at steady state. So, for example, for a correlation around a sphere, for example, whose temperature is different from the temperature of the ambient fluid, you assume that the temperature of the sphere is a constant. The temperature of the ambient fluid far from the sphere is also a constant. Calculate what is the temperature field around the sphere, and then from that evaluate what is the flux from the surface of the sphere. Okay. This is valid provided the system is at steady state, that is that you have a constant temperature on the surface independent of time, a constant temperature far away independent of time, and under those conditions you can get these correlations, whether it is under conditions of diffusion or under conditions of convection. Okay. In both those situations, in convection dominated transport, for example, you assume that the temperature at the surface is a constant independent of time, and the velocity of the sphere relative to the fluid is also a constant independent of time. And under those conditions you can calculate what the correlations are for the temperature field around the sphere, and from that the flux. Now, what if the temperature is a function of time? For example, if a sphere is cooling with time, okay, in that case the steady state approximation is not strictly valid. You can still make the steady state approximation provided the time required for the temperature of the sphere to decrease is much longer than the time required for the temperature field around the sphere to develop at steady state, to reach its steady state. Okay. In that case, to a good approximation, the temperature field around the sphere is the same as what you would have had under steady state conditions, and therefore, you can use the Nusselt number correlation that was derived for the steady state situation. Okay. And we had seen an example of that for heat conduction from a sphere in the last lecture. We took a sphere of diameter d and density and specific heat specified, immersed in a fluid with a difference in temperature which is varying with time, because as the energy is being conducted out of the sphere due to the temperature difference, the energy of the sphere is decreasing, and therefore, the temperature of the sphere is also decreasing. Okay. And we had written a balance equation for that. Okay. We had written this balance equation for that. The rate of change of energy of the sphere, the rate of change of the thermal energy of the sphere is equal to the net energy that is being conducted out of the surface of the sphere, okay, which is the right hand side, which is the product of the flux and the surface area. Okay. And we had substituted for the mass of the sphere the flux based upon the Nusselt number correlation, and from that we got an equation for the temperature variation with time, and that equation is shown here. Okay. That equation is shown here, the rate of change of temperature. Just dimensionally you would expect that the rate of change of temperature has to be a temperature difference divided by a characteristic time, just from dimensional analysis, and the task for us then is to determine that characteristic time in terms of the properties of the sphere and the fluid around it. Okay. And this was the expression we had got for the characteristic time. Okay. It contains the density and the specific heat of the sphere and the conductivity of the fluid. We had assumed that the conductivity of the sphere is much larger than that of the fluid, so that the temperature is uniform everywhere within the sphere, and that is the same as the surface temperature. We will see later how to calculate the temperature within the sphere if that assumption is not true. Okay. And from that we got an exponentially decreasing temperature with respect to time. Okay. An exponentially decreasing temperature, okay, with characteristic time Tc. and we had examined the condition under which the diffusion time is much greater than the characteristic time is much greater than the diffusion time. The ratio of these two was given by the ratio of the density and specific heat. Okay. So, if this ratio is large compared to 1, then you know that the characteristic time for the evolution of the temperature field is large compared to the diffusion time. Okay. Basically, the specific heat is and the density, the product of the specific heat and density is the change in energy per unit change in temperature. If that for the sphere is much larger than that for the fluid, then you can use the steady state approximation for the correlation for the Nusselt number. Okay. And last class we had examined, we had started examining one case where there is a change in diameter. Okay. The temperature field changes not the concentration field changes not because the surface concentration changes, but because the diameter of the particle changes. Okay. So, we so for definiteness let us put some numbers here. Okay. Okay. Camphor particle with diameter d is equal to 1 millimeter, okay, at ambient temperature and pressure. Okay. So, temperature is equal to 20 degrees centigrade. Okay. And the density of camphor rho is equal to 10 power 3 kg per meter cubed. Okay. The diffusion coefficient of camphor in air, okay, is equal to 2.3 into 10 power minus 7 meter square per second. Okay. This is a little smaller than what you would expect for diffusion of nitrogen or oxygen in air or gases in air, because camphor is a large molecule. Okay. It has a molecular weight of I think 152. Okay. So, it is a large molecule, molecular weight is equal to 152. Okay. So, it is a large molecule. Okay. And the vapor pressure in air, the vapor pressure of camphor in air at 20 degrees centigrade is equal to 87 pascals. Okay. And because of the difference in concentration between the surface Cs and the concentration far away, that is 0, the camphor is going to sublimate, and as it sublimates the diameter is going to decrease with time. And what we want to know is that the total, okay, total time for sublimation. Okay, that is when the diameter of the camphor particle decreases to 0. Okay, so, that is what we have to calculate. Okay. So, now the mass of the camphor is decreasing as a function of time. Okay. The mass of the camphor particle is decreasing as a function of time. Okay. So, the mass balance equation is going to be dm by dt, rate of change of mass, is equal to minus the average flux into pi d square. Okay. And note here that the diameter is now a function of time. Okay. So, as the camphor sublimates, the diameter is going to decrease with time. Okay. The mass is given by the density of the camphor particle times pi d cube by 6. Okay. And therefore, dm by dt. Okay. So, since I have d for diameter as well, I will use a double bar on the derivative. Okay. I will use a double bar on the derivative. Okay. Okay. When you write in text form, this is actually text mode, whereas this diameter, the diameter that is used here, okay, is in italic mode. However, since I am using a total derivative here, okay, since I am using d here, okay, so let me just to distinguish, let me write it as a partial here. I will use a partial to distinguish it from the diameter that is being used here. Okay. It is actually a total derivative, but I will just use the partial to distinguish it from the diameter, the same d for diameter. Okay. Okay. This is going to be equal to rho pi d square by 2 times partial d by partial t. Okay. Just differentiating using chain rule. Okay. So, therefore, my equation for the rate of change of the diameter with respect to time becomes rho pi d square by 2 partial d by partial t is equal to minus j a v pi d square. Okay. Therefore, partial d by partial t is equal to minus 2 j a v by rho, and I can use the Nusselt number correlation for this. Okay. The Nusselt number correlation for this case is that Nusselt number for mass transfer it is the Sherwood number correlation. Sherwood number is equal to d Cs by d, okay, is equal to 2. Okay. Sorry, Sherwood number is okay. Sherwood number is the average flux divided by the right side of Fick's law. Okay, the quantity with the same dimension as the right side of Fick's law, which is the diffusion coefficient times the concentration difference. Concentration difference in this case is just Cs. So, the diffusion coefficient times the concentration difference divided by the diameter of the sphere, that ratio is equal to 2. Okay. So, therefore, I can write this as minus 4 okay, d Cs by j a v d. Okay. We have substituted the Sherwood number is equal to 2 in this case. Okay. Okay. Now, you can see that there is a diameter on the left and the right side. Okay. There is a diameter on the left and the right side, and that diameter is a function of time. Okay. So, there is no j a v here. Okay. Okay. The diameter on the left and the right side is a function of time. Okay. So, I have to multiply throughout by d, okay, in order to get d times partial d by partial t is equal to minus 4 d Cs by rho, okay, where rho is the density of the camphor particle. Okay. The left side is equal to half partial by partial t of d square. Okay. Which implies that partial d square by partial t is equal to minus 8 d Cs by rho. And you can integrate this once in order to get d square is equal to minus 8 d Cs t by rho plus a constant of integration. Okay. That constant of integration is determined from the condition that at t is equal to 0, d is equal to the initial diameter d naught. Okay. D naught is the initial diameter, in this case 1 millimeter, okay, which will give us that c is equal to d naught square. Okay. And therefore, the equation for the diameter becomes d naught square minus d square is equal to 8 d Cs T by rho. Okay. Alternatively, d square minus d naught square will have a negative sign. Okay. I just put here d naught square minus d square. Okay. What is the total sublimation time? Okay. T is equal to Ts when d is equal to 0. Okay. That is, the sphere has completely disappeared. Okay. So, that is the sublimation time. Okay. When d is equal to 0, that is the time required for complete sublimation, and you can see that the time required for complete sublimation is going to be equal to rho d naught square by 8 d Cs. Okay. So, that is the time required for complete sublimation. So, for this particular case, what is that sublimation time? Okay. So, let us calculate that. Okay. First thing is, we need to calculate what is Cs. Okay. We know all other quantities. Okay. We know all other quantities here. Okay. The density, the diffusivity, etc. is all given, the diameter. What is Cs? Okay. So, let us calculate that. Okay. From the ideal gas equation of state, Cs is equal to P, the molecular weight, okay, by kBT. Okay. Okay. This is the vapor pressure. Okay. Okay. The molar concentration is P by kBT. The mass concentration is P times the molecular weight by kBT. Okay. P by kBT is the number of molecules per unit volume. Multiply that by the molecular mass, you will get the total number of moles per unit volume. Okay. So, in this case, the vapor pressure is equal to 87 Pascal, okay, into the molecular weight is 152 grams per mole, okay, or 0.152 kilograms per mole. So, 0.152 kilograms per mole, and each mole contains 6.023 into 10 power 23 molecules. Okay. That is 0.152 kilograms per mole, okay, divided by Kb, 1.38 into 10 power minus 23, okay, joules per Kelvin, into T. T is the absolute temperature. Okay. 20 degrees centigrade is 293 Kelvin. Okay. If I had used the molar weight, then I would have to use the ideal gas constant R in the denominator. Either way, you will get the same result. Okay. So, and you can easily see that the result is that this is equal to 5.43 into 10 power minus 3 kg per meter cubed. 5.43 into 10 power minus 3 kg per meter cubed is the mass concentration of camphor at the surface. Okay. And we have just got to substitute this into this expression for the dissolution, the sublimation time. Okay. We have to just substitute this into the expression for the sublimation time to get Ts is equal to rho. The density, if you recall, of this camphor was 10 power 3 kg per meter cubed into d naught square. D naught square is 1 millimeter. So, 10 power minus 3 meters is the initial diameter, the whole square, okay, divided by 8 into the mass diffusion coefficient was 2.3 into 10 power minus 7. Meter square per second into concentration at the surface, which is 5.43 to 10 power minus 3 kg per meter cubed. Okay. And this can be evaluated. You get this as approximately 10 power 5 seconds, which is about 1.2 days. It is about 1.16 days is the time required for the sublimation of this camphor, okay, of diameter 1 millimeter. Okay. It takes more than a day for the entire material to sublime and go into the vapor phase. Okay. For these set of parameters, okay, this for these set of surface parameters and bulk parameters. Okay. And that is the reason that you have to keep camphor in airtight containers, so that it is not exposed to ambient air where the concentration is 0 and does not go on subliming. If you put it in an airtight container, then the concentration becomes equal to the saturation concentration pretty quickly, and after that there is no further evolution. Okay. The last thing we have to do is to verify that in the time required for sublimation, which is basically the time scale for the decrease of the diameter of the particle, is much larger than the diffusion time. Okay. What is the diffusion time in this case? Okay. The diffusion time in this case at initial times is going to be equal to d naught square by the diffusion coefficient. Okay. And you can evaluate this. Okay. This is equal to 10 power minus 3 meters, that is the initial diameter whole square, divided by the diffusivity, which was 2.3 into 10 power minus 7. Minus 7 meter square per second. Okay. And this works out to approximately 4.35 seconds. Okay. So, the time required for the concentration field around the sphere to develop when the diameter has changed is only about 4 seconds, whereas the time required for complete dissolution is about 1.2 days. Okay. And therefore, under these conditions we can assume that this is a steady state process, and therefore, the Nusselt number correlation can be used, even though it is not strictly applicable, because the problem is not at steady state because the diameter is changing. Okay. Even though the diameter is changing, the time scale required for the diameter to decrease is much longer than the time required for diffusion, for the field to develop around the particle, and therefore, we can use the correlation that is derived for steady state. Okay. Okay. So, this is for diffusion dominated flows, where for the flow around a sphere, for the transport from a sphere, okay, whether it is heat or mass transfer, is primarily due to diffusion, and we know that when the diffusion is dominant, the Nusselt number and the Sherwood number are constants. Okay. So, next I will examine forced convection. Now, in forced convection, for example, you have a particle that is moving relative to the fluid, okay, particle that is moving relative to the fluid, okay, and with some velocity v. Okay. And if you look close to the surface, the fluid is getting swept backwards around the particle. Okay. The fluid is getting swept backwards, okay, around this particle. And you could have two different situations based upon the boundary conditions. If this were a solid particle, then relative to the, if you are sitting on the particle center, right, then the fluid velocity has to decrease to 0, okay, at the particle surface. Okay. The fluid velocity has to decrease to 0 at the particle surface. Okay. And if we consider the situation where the Peclet number is large, okay, Peclet number is large for forced convection problems, because convection is dominant compared to diffusion, okay, when the Peclet number is large. Okay. However, even when the Peclet number is large, okay, if you go very close to the surface of the particle, if you go very close to the surface of the particle, there is convection due to the fluid flow along the surface. However, there is no convection perpendicular to the surface, okay, because of the no penetration condition at the solid surface. There is no flow perpendicular to the surface, and therefore, there is no convection perpendicular to the surface. Okay. So, ultimately transport perpendicular to the surface has to be due to diffusion, okay, in the case of solid particles. Okay. So, you have a situation where material is diffusing out from the surface, say, okay. Okay, if we assume that the surface has a higher temperature or a concentration with respect to the bulk, the material is diffusing perpendicular to the surface and it is being rapidly swept downstream, okay, due to the strong flow. Okay, it is being rapidly swept downstream due to the strong flow. And in this limit, you have to incorporate diffusion close to the surface, even though the Peclet number is large, because ultimately transport perpendicular to the surface has to take place due to diffusion. But once it diffuses perpendicular to the surface, the strong flow is rapidly sweeping the material downstream, and therefore, the change in concentration due to diffusion from the surface is restricted to a thin region close to the surface. Okay. It is restricted to a thin region close to the surface in the limit of high Peclet number. Okay. And the thickness of that region is actually much smaller than the particle size. In this case, the characteristic size is the particle diameter. Okay. So, in the limit of high Peclet number, because material is being swept rapidly downstream as soon as it diffuses from the surface, diffusion length scale is actually much smaller than the particle diameter. Okay. The length scale for diffusion, for example, for a solid particle where I have a no slip condition at the surface, so that the velocity has to decrease to the 0 at the surface, the length scale for diffusion is equal to the Peclet number per minus 1 by 3 times the particle diameter, okay, the characteristic particle diameter, if there is a no slip condition at the surface. Okay. On the other hand, if I had a gas bubble, for example, okay, if I had a gas bubble, for example, where I had a non-zero velocity at the surface, okay, once again, as there is fluid flow around the surface, okay, as there is fluid flow around the surface, okay, the diffusion of mass, let us say gas mass or energy from the gas which is at a higher temperature, that is going to diffuse perpendicular to the surface, that is going to transport perpendicular to the surface due to diffusion, and it will be rapidly swept downstream due to convection. Okay. And in that case, the characteristic length scale is equal to Pe per minus half times d. Okay, that is the characteristic diffusion length scale in that case. Okay, for transport from a gas bubble, these two are in the limit of Peclet number much greater than 1 and Reynolds number much less than 1. Okay. If I have a laminar flow, but a high Peclet number flow, okay, where the convection for heat and mass transfer is dominant compared to diffusion, then these are the length scales, okay, for diffusion, okay, from the surface. And of course, the time scale for diffusion, okay, the time scale for diffusion has to be equal to the length scale for diffusion the whole square divided by the diffusion coefficient, okay, that is a characteristic time scale for diffusion. This diffusion length and this diffusion time has to be much smaller than the time required for evolution of the temperature of the particle if we are to use steady state approximation for forced convection problems. Okay. So, this is only for Peclet number large compared to 1 and the Reynolds number small compared to 1. Okay. You have other relations when the Peclet number is large and the Reynolds number is large, but for a laminar flow, for flow around a particle, flow through a pipe. Okay. I will discuss all of those length scales one by one in the next lecture, so that we have a clear idea of under what conditions we can use a steady state approximation for the diffusion process in a situation where the temperature at the boundaries or the dimension of the boundary is varying, is evolving in time. Okay. obviously you can use it when the diffusion time is much smaller than any other time scale in the problem. Okay. So, we will do the same, I will discuss the same issue. I have discussed it for a particle with no slip condition and a mobile interface and a static interface with no slip condition and a mobile interface with a slip condition at the surface for large Peclet number and for laminar flow at small Reynolds numbers. We will discuss it for other situations, flow past a flat plate, flow in a pipe, and then we will solve some examples of how we can actually evaluate the variation in temperature with time using a correlation for the evolution of for the average flux, instantaneous average flux, assuming that that instantaneous average flux is the same as what you would have had the system been at steady state. So, we will continue this discussion in the next lecture. I will see you then.